Okay, so let's start the talk. We'll start with the universe. To get an idea of the universe is about 15 billion years old. There's around 150 billion galaxies. Each galaxy has around 300 billion stars. You do the maths, that's a huge amount of stars, a huge amount of material. And as physicists, as scientists, if we're trying to understand all that material, that can appear to be quite daunting. However, what one can do, one can take a step back and just try and look at things from simple principles. And when one does that, things can start to look a bit easier, a bit more simpler. So what do I mean by that? Okay, I'll give you an example. The example I'll give you an example by posing this question to you. The question is, how many elementary particles does it take to describe the matter around us? So all the matter around us, as far out as the universe that we observe, if I wanted to reconstruct that with distinct elementary particles, how many do you think it would need to build the universe that we see around us? Any ideas? Feel free to call out. Feel free to call out, guessing? Anyone? Okay. Very good, very good. You could take 4, however, I'm arguing 3. So the 3 that I believe it will take, I will show you what I mean. So we've got matter particles, and we could categorize matter particles into categories, and one of these categories are called quarks. We've got 2 quarks, which I believe we need. We've got the up quark and the down quark. So the up quark has a charge of +2/3, down quark has a charge of -1/3, and those are the quarks which we use to make things like protons and neutrons. The other type of matter particle is called leptons, and the third particle that you need is a particle we're all familiar with. It's the electron. So the electron is a lepton, and it's elementary in that it cannot be broken down any further. It's not composite. So let's look at some material, some familiar particles. So you all know about atoms, and you construct atoms together, build molecules. You've got the periodic table. With that periodic table, you can construct all kind of materials. So we've got the electron, as I stated earlier, which orbits around the nucleus, and your nucleus is a construction of protons and neutrons. However, the protons and neutrons are not composite. I'll take a little aside here, and what I've done is also I state the masses of these particles. So we've got an electron, which is a mass of 0.5 MeV. We've got protons and neutrons, they're around about 1,000 MeV. 1,000 MeV we also refer to as a GeV. So the knowledgeable and the astute of you will realize I said, okay, we're going to look at the masses of these particles. However, I state the masses in energy. So you can say, wait a minute, isn't that contradictory? No, it's not, because of this equation, E = mc². That's Einstein's equation. And what it says is really energy and mass are equivalent. And energy is way more informative than the mass units of kilograms. For example, like conservation of energy, that's very, very informative. It tells me I know the mass of a particle based on its conservation of energy. I know what it can decay to, what it can't, just by that alone. So from now on, you'll never see units like kilograms, whatever. Units of energy is what we'll work with from now on. Okay, so let's get back to my argument of 3 particles. So the electron, I said, is an elementary particle, but then these protons and neutrons. These protons and neutrons, they're composite. What they are is the proton is 2 up and a down quark. You do the maths, 2 ups and a down quark, that gives you your +1 charge that we see with the proton. Neutrons are 2 down quarks and an up quark. You do the maths again, you get a neutral particle there. And they're composite, confined to a space of what we believe to be about 10 to the -15. So they're just whizzing around in this composite state. So those are the 3 particles. I could kind of understand the 4, and maybe the 4 comes in that you say, okay, you've got these 3 particles, and maybe the photon is the 4th, light. But that's, so I'll buy that. You can't see anything without light. Light is what you use to see particles. So maybe I could take that, but my statement was matter particles, to construct matter. So for matter, these are the 3 particles you need: your up quark, your down quark, and the electron. So I was talking about the energies of protons and neutrons. I was saying they're around about a GeV, 1,000 MeV. So there's lots of experiments one can do to measure the masses of these particles, but there's also very simple things one can do. And you know about wave-particle duality. You know that basically particles can behave like waves, and you know that low momentum objects, they have larger wavelengths, higher momentum objects have shorter wavelengths. You know, from the Heisenberg uncertainty principle, basically I said that these objects were confined to a space of 10 to the minus 15. 10 to the minus 15 meters, you plug it into the Heisenberg uncertainty equation, you get a momentum stroke energy of around a GeV, and that's consistent with what we see with protons. Protons around a GeV, confine particles to a region of that space. That's the kind of energies that you're dealing with. Okay, so what we want to do is, in order to understand these particles and how they behave, we want some kind of theory, some kind of model to be able to describe them. So what we come up with is a quantum field theory that we refer to as a standard model. So again, what I said before, quantum field theory is like the whole universe. You know, it's quite a daunting. It's quite daunting when you mention it. However, let's take the same principle in that we can look at just some simple principles, and things from that perspective are not as complicated. So, like I said, some simple points. So let's look at some simple points of a quantum field theory. So the interactions are described by underlying fields. That's what we mean by interactions. We've got some underlying fields. The quantum, that simply means that you've got discrete states, not all values are allowed. So the interactions are not continuous, all values are not allowed. The field communicates via particles. So we have a field, we have an associated particle. So that's also important, and it shows what the value of the Higgs boson was, because you have a Higgs field, so there should be a particle associated with it. So when we consider forces between particles as an interaction, there must be a particle associated with that force that transmits the force. So what we'd like to have is a quantum field theory for the four fundamental forces that we're aware of: the strong force, the weak force, electromagnetism, and gravity. The issue is, the standard model itself, it describes everything but gravity. So we have a standard model, which is a quantum field theory for these three forces and not gravity. So I introduced to you the three matter particles which construct the universe as we observe it. However, there's more. So we've introduced you to the up and the down quark, leptons, the electron, the familiar particle, the particle we're all familiar with. But there's also particles called neutrinos. Neutrinos are a weakly interacting particle, very abundant, constantly bombarding through the Earth, bombarding through us now, but they're so weakly interacting that they just don't interact with us. Then you can move to what we call the next family. You have charm quark, strange quark. Charm quark behaves like the up quark, same charge, 2/3. Same with the strange quark, behaves like the down quark, has a charge of -1/3. Properties are all exactly the same, except for, let's look at the masses. The masses are so much heavier than these particles. And because the masses are so much heavier, they're unstable. So why is it unstable? Because it's so much more energetic. It's more energetic because it has that energy gives it a lot more choices. It has the probability to do lots of other different things is increased, and it's increased to the extent, such an extent that it's unstable. The decay will always move to something else and decay down the line, and that's what the masses enable it to do and make it unstable. Similarly, a higher family, you've got muons, same properties as electron, but heavier, as again a consequence unstable. Third family, you can see that the pattern is that these families are getting heavier in mass. Top quark, huge mass there. Bottom quark, again, same properties, but just unstable. And then finally, with the leptons, you've got the tau lepton again, same properties as the electron and the muon, just more massive, and the tau neutrino. So those are the matter particles, which we call fermions, and they interact with other particles via force carriers, bosons. So the strong force, which you see in nuclear interactions within the nucleus, the strong force carriers are called gluons, and we believe there's 8 of those, and they're massless. the electromagnetic force as far as electromagnetism. The force propagator there is a photon, and light is an example of a photon. Light is just a photon in a particular frequency range. Then the weak force carrier. The weak force carrier has two W's, W plus, W minus, and a neutral boson, the Z. And in this case, they're quite massive particles, and it's that mass, the heavy nature of them, is what essentially makes the force weak, and I'll explain a little bit about that later. Okay, so let's talk again about some particle properties. So particles, they're described by properties. They have things like mass, charge, intrinsic spin, which is quantized. You can have whole unit spins, and they're called bosons. You have particles called fermions, which have shifts by steps of halves, and they interact with specific forces. So instead of talking about matter and forces on a quantum level, what we'd like to talk about is fermions and bosons. So another question, does anyone know who this person is? I'd be surprised if anyone does. Okay, well, I believe that we should all know who this person is, because this is someone called Emmy Noether. So the idea is, I thought it was International Women's Day on Sunday, and I thought, okay, bring a woman into a woman who's played a significant role in physics into the talk. However, she should be in anyway, because initially she's a mathematician, but her contribution to science and physics is huge. And for me, she's one of my favourite mathematicians of the last 100 years, or if not ever, and I'll explain to you why. Because she produced lots of mathematical theories. One of them, the most famous one, is a really complex mathematical proof, but then the conclusion to that proof is really simple but fundamental to science and definitely particle physics, and it's a conclusion that we all know. And it basically says that if you have a symmetry, then you must also have a conservation law. And it's the conservation laws that we're all familiar with and we all take for granted. Let me give you an example. So a symmetry under translation equates to conservation of momentum. So in physics, we always start conservation of momentum, and we work from them. There's all sorts of beautiful things that we can prove and disprove based on conservation of momentum. But why is momentum conserved, and how is it conserved? And Emmy Noether proved it mathematically. And basically, let me give you an example. So you have an electron. Electron has its behavior in space X. If I move an electron to a different position, it's still an electron, it still has its properties, nothing's changed with that electron just because I moved its position. So that is a that's a translational symmetry. So it's symmetric under space. And because it is symmetric under that translation in space, that implies conservation of momentum. And she proved that mathematically, and conservation of momentum, yeah, it's huge. Symmetry under time translation. I've got the same electron, it has its properties. If I come back to it at a later time, its properties are still the same. It still behaves the same, it's no different to how it was at the time earlier. So that's a symmetry under time. And that symmetry under time, that implies conservation of energy. Again, that's, it's the crux of many proofs and many experiments, conservation of energy. But we just take that for granted. Energy is conserved, and we proceed from there. But there's mass behind that, and that comes from conservation of time translation. Sorry, symmetry in the time translation. Another symmetry under rotation. That's conservation of angular momentum. Again, we're told from a starting point, angular momentum is conserved. But we know that because symmetry under rotation exists. So, you've got your electron, you rotate it, it's still the same electron, its properties are still the same. That is a symmetry under rotation. And the implication of that, because Emmy Noether proved it mathematically, is that you have a symmetry, then there's an associated conservation that goes along with it, and that, in this case, is angular momentum. So in physics, we see these symmetries, and because of these symmetries, we know that something is conserved, and we can work out what that conservation is. And conservations are fundamental for physics, especially particle physics, because that's how we predict how particles will behave. Okay, so we can put all this together, and we can start to understand what to expect and what we can do. And for example, I talked about all these heavier particles. However, they're unstable. How do I know that they exist if they're unstable, if they're always quickly decay? Well, we create them in accelerators that Tom mentioned. And how do we create particles? Well, we create them from energy at colliders like CERN. However, like we say, we've got these conservation laws. We mustn't violate these conservation laws like charge, momentum, etc. So from energy, which we want to create these particles from, we know the starting point, energy doesn't have charge, doesn't have angular momentum. So I've got to finish with a state that doesn't have charge and doesn't have angular momentum. So if I was to create an electron, I know an electron has negative charge, it has internal angular momentum, internal what we call spin. So I must balance that because I need to finish off with a final state that has no angular momentum, has no charge. So if I create an electron with a negative charge and a particular angular momentum, I must also create a particle with opposite charge and an angular momentum in the opposite direction. So a particle with positive charge, same mass as an electron, opposite angular momentum spin to an electron, that's a positron, that's antimatter. So essentially when I create matter, I must also create antimatter. You know, when I was a kid and I heard of antimatter, I thought antimatter was science fiction, but antimatter is no more science fiction than matter, because every time you create matter, you must also create antimatter. You've got to balance, you know, laws have got to be conserved. Okay, another question, I guess people may know who this is. Anyone know who this is? Feel free to call out. Feynman. Exactly, it's Feynman. So Feynman's famous for many things. One of the things I'll talk about today that he's famous for is his Feynman diagrams. So Feynman diagrams, essentially they just show particular decays that they show, and particle physicists, we write down all the Feynman diagrams for all the possible decays and work out the probability of them taking place. With Feynman diagrams, there's always an implicit time and space axis. So in this case, what we have on the Y here, we have space, and sorry, on the X we have space, and on the Y we have time. So what we have in time 0, we have two electrons separated by some distance in space. As we move up in time, they move closer together, and then at some point, this is a photon, is exchanged, and then they move apart. So what this diagram is, you know, it looks an obscure diagram, but it's a diagram for electron repulsion. And I have an illustration here which shows you've got two electrons, they move close together, a photon's exchanged, and they move apart. Classically, we've always been told you've got two electrons, there's a field, and in that field, electrons repel each other, full stop. And you know, you're supposed to be happy with that, and typically you are, and you move on. However, that's not the full story. The quantum explanation is that you've got two electrons. What happens is one electron will exchange a photon with the other electron. The electron that emits the photon, let's say emits the photon in the forward direction, that photon's got momentum in the forward direction. In order to balance momentum and conserve momentum, that electron's then got to move back in the opposite direction to conserve momentum. The other electron which absorbs this photon then receives that photon and its momentum in that direction, so then it continues to move. So then it moves in the direction same as the photon. So that's why the electrons change, and that's why they feel what we see as they feel the force. Essentially, it's photon exchange, and that photon is transferring momentum. Okay, so there's more Feynman diagrams here. This is the Qs or quarks. So you've got two quarks, they're being repelled by a gluon. Gluons themselves feel the strong force, so this is actually gluon scattering. So gluons themselves will experience forces via gluon exchange. Also elaborating on more properties of the strong force, in that quarks themselves, they feel the strong force, but part of the properties of quarks is that they don't exist in isolation. And there was an experiment called DAISY. Well, there's an accelerator called DAISY in Germany, and some of the experiments there, what they would do, they would fire electrons at protons to essentially understand to probe the properties of a proton. And what you could do, you could fire an electron at a proton with high enough energy that it would push out a quark from the proton. However, I said that quarks can't exist in isolation. So what happens is that energy that you use to free the quark, part of that energy goes into actually creating quark-antiquark pairs, which this free quark will then tag onto. So that quark can still be, you can hit the quark with such energy that that quark can still have enough energy to free from the pair that it joined onto. But then again, you need to create more pairs so that it doesn't exist in isolation. And you can keep creating pairs of quark-antiquarks until the energy you put in expires. And this is an illustration in that what we do here is you fire an electron, it hits a quark, that quark's freed, but with that energy that you put in, pairs were produced, it's freed again, but more pairs are produced, and it can keep happening until, like I say, that energy that you input with the electron expires. So it's part of the properties of quarks in that they're confined. It's called quark confinement. Okay, so mentioned the electromagnetic force, mentioned the strong force, now the weak force. You may be familiar with the weak force as far as beta decay. Beta decay, for example, the neutron decay into a proton, electron, and an antineutrino. So there's lots of radioactive nuclei which will decay via beta decay. And what you see here, you've got a nucleus and electrons orbiting, and then in the beta decay, one of the nuclei will change to a proton and emit an electron. So, as I mentioned, it's a weak process, and you look at the neutrons. I'm talking about all these other decays which happen in 10 to the minus 10, well, even less seconds. Whereas the neutron can last for 15 minutes because it's a it decays by the weak process, and it's a weak decay. So what you've got is a neutron, which suddenly disappeared, but shouldn't have done, and essentially it turns into a proton, electron, and an antineutrino. But really, what's happening from a quark perspective is it's a d quark within the neutron, decays to an up quark, and emits an electron and an antineutrino. The Feynman diagram looks as follows. You've got a d quark, moves along, emits what the weak force carries, which is a W, and then that decays to electron neutrino, and your quark, now it changes to up quark. You do all the maths as far as conserve the charges, and they add up at the vertex. All the charges add up. Okay, so the question is, why is the weak force weak? I alluded to it earlier. It's because the force propagators, the particle propagators are just so massive, in that what you're really doing, you're exchanging the particle between the two bodies, and in this case it's a huge W boson, and the probability of doing that is low. So I can give you an example of, well, actually what we can do even better is I talked about these Feynman diagrams, and what they do, they illustrate the particular decays that take place. But the theorists, what they do, they identify the possible decays that can take place, but actually the decays themselves, you can look at how they proceed, and you can look at the steps, and each part of the step is a probability, and you can actually calculate the total probability of that decay, and that's what the theorists do. They use these Feynman diagrams to calculate the probability of decay. So what we can do is look at Feynman diagrams, and from these Feynman diagrams they can have an idea of how we calculate the decay, but also compare the weak and the electromagnetic force. So we could compare two decays. These are two decays, however, the initial and final state are the same. What you're actually doing is producing muon pairs, and if you remember, muons essentially like electrons, but just a heavier electron state. But a little bit perverse here, and I've changed the axes on the Feynman diagram. Now the y-axis is space, and the x-axis is time. So this is muon pair production, And that prior to CERN, what we had is an accelerator which would collide electron-positron pairs to create newer particles. So what we would do is collide electrons and positrons. We keep upping the energy so that we can create heavier and heavier particle states. That's how we know about lots of those particles that I was telling you about. You know, you could create muon pairs, tau pairs, B pairs. And in this case, this is the Feynman diagrams for muon pairs. And these can be produced electromagnetically and also weakly. However, as a theorist, you do the calculations of these diagrams, and you'll see that this diagram at low energy is way, the probability of this diagram is way higher than this. And I'll explain why. So, Feynman diagrams that illustrate the components of an equation. So I'll try and go through this with you. So we can label the components. We've got the incoming components, which are 1 and 2. They're the same for both diagrams. You've got two electrons, you've got electron and positron going in at the same energy. You've got the outgoing components. Because they're going at the same energy, the muons, as they leave, they can't have any more energy than the particles that went in. That energy is conserved. So in both cases, 3 and 4, they're the same in both cases. You've got the vertices, where these particles annihilate and pair produce, 5 and 6. Slightly different in that you've got a photon connected here and a Z connected here, a photon producing here and a Z producing here. 5 and 6 slightly different. However, you do the maths, the difference is negligible, so we can just say, forget that. So far, the only difference is 7, which is the propagator, is the force propagator. You've got a photon here and a Z, that's the difference. So I've been through that. And what you do to calculate the probability, you multiply all those components. There's a mathematical term for each component, and you just multiply them all, and that gives you the amplitude which relates to the probability. So like I said, there's only a slight difference between the vertices, 5 and 6. It's the propagator, 7, which is the real difference. So for the weak, you have to create a massive propagator, which I've talked about earlier. For electromagnetism, it's massless. You don't have to create a massive particle, and that is where the difference lies. And again, I'll try and explain that now. In that for the Z boson, we say it has a mass of 91 GeV. There's a little bit of information we're leaving out here, in that when we say it has a mass of 91, what we mean is it has an average mass of 91. It has a range. The distribution of the Z boson is wide, and the average value is 91. So the probability of producing at low energies a Z boson is low at low energies. And that's what contributes. So this is the probability distribution of the Z boson. So what you can see is at low masses here, the probability is really low. Once you get to the mean value, it shoots up, and that's where the probability is really high. So if you had the energy around the Z boson mass, then the probability of this diagram rockets. And it's interesting, if you look, and there's lots of diagrams where you collide electron-positron pairs together at different energies, you see as you move up in mass, the probability goes down. I'll show you because there's a term in there. But then as you get to the Z peak, you get a massive peak around the Z, and it drops again because the probability of producing. That's where this contribution turns on, and then it drops again, and it goes down. Why? You'll be able to work out that distribution which I just explained, because I can show you the maths of this term 7. Term 7 is this. This is the propagator term. Basically, ignore the numerator for now. The denominator, this p squared, essentially it's the momentum squared minus the mass squared. So in the case of the photon, the mass is 0. So it's much higher than the case of the weak interaction. You've got the mass of a Z, which you've got this massive particle. So at lower energies, this Z propagator is way lower than the photon. And that's what makes this diagram so much weaker. However, what you could, if you notice, if the energy or the momentum squared is equal to the mass, then this approaches 0. You've got 0 on the denominator, then this term just shoots right up. And that's what determines that peak around the mass. So this mass of the Z, when the momentum or energy gets around the mass of the edge, you get this huge contribution from this term. Other than that, away from that, the contribution is really small. So that was an example of how we use Feynman diagrams. So I showed you the mathematical term for term 7, but we have terms for 1, 2, all of them, and you add them together to work out the probability. Okay, I'm running out of time, so let's speed up. So this is what we call the standard model. These are all the particles in the standard model. So combining all these particles together, like I said, that's what our model of particles and how they interact. However, there's one particle I haven't mentioned yet, which is integral to all the standard model, and that's the Higgs Boson. I won't say too much about that because Christian will talk about it a bit more later today, this afternoon. Okay, let me say one thing, it's just that basically things like the Higgs boson, they're more massive than other particles. What that simply tells us is that they're coupling with the Higgs field a lot more than the other particles. So the more massive a particle is, the more it's interacting with the Higgs field. That's what it's saying, and that was always in the standard model. That was always in the standard model, you know, in the 60s. We explained that there's a field coupling with these particles, and that's what gives them the mass. And in order to prove it, if you remember what I said, if there's a field, there's a particle associated with it. So that's what the hunt for the Higgs boson was, is that we've got this model that works beautifully, but we claim there's this Higgs field. So if I'm claiming there's a Higgs field, there must be a Higgs particle. Show me the Higgs particle. And that's what the big drive was. And unfortunately, we found the Higgs particle, and that's what confirms this standard model. Okay, we'll skip through this because of time. So the standard model describes particle interaction. This model we have, it describes particle interactions to a really high precision. I think it's still today the best agreement between theory and experiment is the standard model. I think you've got quantum electrodynamic predictions, which go to something like nine numbers after the decimal place, and the experiment agrees with it to that level. However, there's some issues. I mentioned one earlier, there's others. Does anyone want to call out what the issues with the standard model are? I mentioned it earlier. Exactly. That's the real big crunch to it. I'm talking about a model which describes forces and their interactions on a quantum level, but you know there's no gravity in there. If you say show me the Feynman diagram for gravity, I'll say sorry, we don't have one. So that's a huge, massive hole in this, you know. So gravity, that's a real problem with the standard model. However, don't misunderstand what I'm saying. That doesn't mean we don't have a good understanding of gravity. Our understanding of gravity is impressive, not via the standard model, it isn't though. We have a separate theory for that. It's not my domain, but we have a different theory, and that theory is general relativity. That's Einstein's theory of general relativity. It's not a quantum theory, it's a completely different theory. Still, it's impressive, and I'll show you why it's impressive and how we're able to understand the universe around us with general relativity. Again, this is not my field, but still, I don't want to leave you thinking we know nothing about gravity, because that will be a wrong message to send. So I want to send the message we do understand gravity. We can explain gravity quite well. So this is an image, a beautiful image taken by the Hubble telescope of a cluster of galaxies. We look at this cluster of galaxies and we analyze it in depth, and then we start to see problems. And that problem is we see a particular galaxy, but we see 8 different times in space, like parsecs apart. And by the same galaxy, I mean the exact same galaxy. You know, a star explodes in that galaxy, it explodes 8 different times. Everything's happening at exactly the same time. You know, and we're not aware of parallel universes that are happening simultaneously. There's something wrong there. We can explain it with general relativity. If you look at this image, this is a side-on image, this is Earth, this is the cluster of galaxies we're looking at, and what we have is a black hole in between us and that cluster of galaxy. Let's look at one galaxy. Light would shoot normally away to somewhere else, and that wouldn't come to us, but we've got a black hole that bends this light back to us, and we see it at Earth. So now we see that galaxy. whereas previously we wouldn't have. Light going in another direction is also bent back, and it comes to Earth, and we see it again. So basically, we've got all these images of the same galaxy being bent back to us, and we seem to see it in different places, but there's only one galaxy just being bent to us by a black hole, and we can explain that perfectly by the maths of general relativity. Another example, gravitational waves. So there's an experiment called LIGO which looks for gravitational waves. And what LIGO was able to detect was two black holes. Each black hole was around 30 times the mass of our sun. And these two black holes are spinning around each other at 250 times a second. So you can imagine the energy that's within that system. You know, that's just a crazy thing to imagine. So they're spinning around each other and they're emitting gravitational waves. And we're able to detect those gravitational waves here at Earth. And the way LIGO experiment did this is a really clever experiment. They just basically use the principles of waves, constructive and destructive interference. They have two lasers. They just shine two lasers in phase with each other, and they bounce, have say a mirror, n number of wavelengths, bounces, comes back, n number of wavelengths, they meet, constructively interfere. Simple physics, no problem with that. Okay, so then these two lasers bouncing back and forth, constructively interfering, let's just take one of them and let's bend it at let's reflect it at a right angle. Again, n number of wavelengths, and it comes back, and because it's n number of wavelengths, constructively interferes, fine. But now we've got a gravitational wave that's compressing space-time, that's moving along this direction. Let's say this direction is the y direction, this direction is the x direction. Space is being compressed along the y direction. So lasers moving back and forth in this direction, compression this way, it doesn't change the wavelength in this direction. But then this additional wavelength that's got an extra n number of wavelengths, the gravitational wave compresses space-time in this direction. The wavelength's compressed, it comes back, it hits the mirror, bounces back, it's no longer in phase. So the constructive interference has changed. And you can see this interference changing essentially 250 times a second. So they're able to detect this. Essentially, they were able to watch these two bodies slowly move around each other as they get closer, spin faster, 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 until they collided and exploded. And they were able to see that spin up, explosion, point satellites, observations in that direction. You were able to see the explosion via gamma rays and radio waves. They were able to observe that. And they've been able to see more. Okay, I really need to finish because I'm overrunning. So, you know, we can't explain gravity as a quantum field theory. Big hole in the standard model. The problem lies in the standard model there, so that's what we're trying to correct. The graviton hasn't been found. However, you know, we know so much, but yet so little. There's another issue, which is the missing matter. And again, gravity plays a part in us understanding that. Just finish with a quick example of the famous bullet cluster. Again, we're looking at clusters of galaxies. The blue and the red is what we highlight. You know, that's not the image. We've just added that to illustrate an issue. The red is what we can observe through, you know, radio waves, photons. That's a material we can detect by those methods. The blue is the material out there that we can detect via its gravitational effects. We know the stuff there because it's emitting gravity. There's things are orbiting it. We can tell there's an amount of material there. We look at this two clusters of galaxies. They move into each other and they collide. They collide. The stuff that we can observe through radio waves and gamma rays, etc., that red stuff just collides and stops. You know, typically what happens in a collision. The stuff that we can detect via gravity, the blue, passes right through each other, just keeps moving. We can see it's weakly interacting. You know, that's fascinating, interesting, but the real fascinating factor is that the majority of that cluster is the blue stuff. So most of the stuff out there in the universe is this weakly interacting dark matter that we can't observe. So that's a real issue, that most of our universe, as we see it, is stuff that we actually don't know what it is. So I will finish now by saying we've got a really good understanding of physics. Our understanding has grown, especially with the discovery of the Higgs Boson. It's helped confirm the standard model. Though there's some interesting questions still to be answered. What's dark matter? What's dark energy? Didn't have time to talk about dark energy, but that's essentially we see the universe expanding rather than contracting because of what's what we'd expect because of gravitational effects. SALXC is taking data. It's not right now, and we'll see in the live link, which shut down. It will be taken soon. In the live link, we'll hopefully have some colleagues who will be down at the experiment I work at, CMS, via taking questions. But it's going to start up again, and when it starts up again, hopefully we'll be able to answer some of these questions. Okay, that's where the talk finishes.
Thank you, Manny.